of this webinar with the recording of this, so don't worry if you can't stay until the end or if you missed it. It will also be available on YouTube, and all participants who require it just will get a certificate of attendance so that you're in order on that one. So what's the topic of today? As the title says, it's remote monitoring and control about thermal desorption, and our guest today is Mathieu Petitjean. Mathieu has been working for Hamers for a couple of years now, I think, and as an engineer, he's been focused quite a lot on how to bring data into the system and how to improve the way we follow up and how we know stuff and how we can automate our thermal desorption work. I'm not going to spend much more time on the introduction since we've wasted already a little bit of time. So I think the floor is yours. I may have some questions as we go on, and the format allows it. So Mathieu, I think the floor is yours. Go on and.
Okay. So first of all, thank you for attending. Feel free to drop in the chat any question that you might have. Jan may interrupt me while I talk. You do not have the opportunity to do so, but drop your questions. I'll start over with a company overview. Many of you, I'm sure, are regular followers, so you will not learn anything, but still, I have to do it. And then we'll dive in with how we model the treatment, how we use this modeling to how it's used with autonomous burners to leverage all the data that we can get, and quite rapidly conclude. So first of all, company overview. You probably most of you know us very well, but as a recap, so we are a technology provider of thermal desorption. We are based in Belgium. We own here in Belgium our lab, our R&D facility, but we do have worldwide operations. The burners that are manufactured here in Belgium are used all over the world to make soil clean. Time to go to the next slide. Of course, it's not working.
There we are.
There you are. So, a non-exhaustive list of our partners that we have the opportunity to work with those last years. You may recognize yourself. You may not be in the list even if you work with us, but we are very popular. And so, as I mentioned, we do have worldwide operations, and that's actually quite relevant to the topic of today, because we are a small company based in Belgium. We manage projects that are located very far away, so it's really critical to have the ability to properly follow up and act. To dive into the principle of the technology, thermal desorption, the principle is quite simple. You will transfer heat to the polluted soil until its temperature rises to the point that the pollutant is vaporized. This pollutant is extracted from the soil thanks to a slight vacuum that is applied to it. And then this pollutant, depending on its type, can be immediately reused or treated accordingly to its type. So keep in mind this picture because I will come back to it with more details. These heating tubes can be placed vertically into the soil. We call it ISTD, in situ thermal desorption, where the tubes are directly inserted into the polluted medium without any need for excavation. If excavation is required by the constraints of the site, we are also, of course, able to do it when the tubes are going to be placed horizontally into a pile of excavated soil.
I can interrupt it. I guess when you mean horizontal and vertical, it's just reverse, right?
It is indeed a typo on the slide. Okay, so that was it for the more general introduction. So now we are going to dive into the real topic of today. I wanted to show first one quote, imaginary quote, but one you have for sure already have heard. The treatment is complete as soon as the target treatment temperature is reached. You have heard from every thermal remediation company, including us. That is true, but that does not tell the whole story. What I mean by that is that it is a safe bet. Indeed, if you reach the target temperature of vaporization of the pollutant, you have the certainty that all the pollutants have been dissolved. But you overlook some factors. You overlook that the soil is not homogeneous. So you can have hotspot of contamination, but also you can have spots in which the contamination is really low. So it may not be required to reach the same temperature in every spot. Also, there are additional physical mechanisms. For example, steam stripping, where the pollutant is carried away by the water vapor that is extracted from the soil. So it's all kind of mechanisms that are overlooked if we only look if we only consider the temperature. So this makes the over treatment suboptimal.
Yeah, I think it's a very important point, because indeed, like I said myself, hundreds and hundreds of times, that's the whole point, is to reach a temperature, because it gives the guarantee that the soil will be clean. The drawback of that is that we are probably spending too much energy. We are injecting too much energy because we just overkill. The result being that everything is clean, you take a safe bet. And indeed, many other mechanisms have explained why, even while we were not reaching the right temperature, you still achieve the goal. And I'm quite interested in listening to the rest.
So I told you I would go back to this picture. How exactly, knowing what we just discussed, how can we monitor the real progress of the treatment if we want to take into account more temperature? Well, the place that we have to look at is in the vapor tube, because it is where all the polluted vapor circulates. Mm-hmm. And what we expect is, as we are treating the soil, contaminants are coming in the vapor phase. They are extracted, and of course, at a certain point, we expect the concentration of contaminants in the vapors to reach zero, as there is nothing more to dissolve. And actually, that's exactly what we did in a laboratory setup. So bear with me to follow this graph. They are not really complicated. Just first have a look at the top picture, the top graph, where the cold point in the soil, its temperature is monitored, which is what is typically done in thermal remediation. Temperature is going up after the heating started. It will have a bit of a steady phase at 100 degrees when the water is evaporated, and we are steadily reaching the target temperature of 250 degrees. It is maintained for a while, and then the treatment is considered complete, and we stop it. Now let's have a look at the graph in the bottom, where we placed an organic compounds sensor directly in the vapor circuit, as I showed on the previous slides. And it behaves as expected, where directly as we start heating, we have a very high concentration. The straight horizontal line actually is the sensor which is saturating, so we already reach a high concentration. And as the treatment progresses, this concentration is going lower and lower over the time, until we reach a point where the concentration is equal to what it was before we started heating. So basically it means that we are not measuring anything more. And if we apply this logic, we could actually shut down the process as soon as we are not recovering any pollutants. And if we compare it to the standard procedure, we could win about 20% of heating time and 20% of power.
I think this graph is very interesting because it indeed shows something that we may have seen, but not always being able to interpret. In this case, it's clear because you can definitely measure the organic compound. Sometimes it's degradation products, so it's a little bit more complicated to see that. But this shows very clearly that also from day one, there is a hell of a lot of organic product that is extracted, because sometimes we forget that very close to the heating pipe, the temperature is already pretty high, and we misinterpret the temperature line, which is that at the cold point, with the average temperature of or the actual temperature in the volume. So it shows here very clearly that as soon as we start the system, there is a lot of recovery that is taking place.
Indeed. That's also striking for the 100 degrees plateau, where we typically associate it with water only.
Yeah.
But that's not true.
Yeah. It's also a common misunderstanding. I've heard often saying, yes, but why don't we need to treat the vapors as we are still at 100 degrees? But the fact is, we are not at 100 degrees. We measure 100 degrees at the cold point, but there is a hell of a lot of soil which is already above 100 degrees and starts to generate it, and this shows it pretty well.
That might be the topic of another webinar to dive in. Now, let's take this information we got from the lab and try to leverage it on the site. It means that ideally, and that is this drawing is from one of our latest patents that have been published. I encourage you to go and read it if you can survive the read of the patent. What you would want in an ideal world is each burner that has dedicated sensors in its paper tube. It would analyze exactly the kind of measurement that we just showed you, and this combined to the data on each pollutant that we can already do in the lab, and also from historical data of all our sites, feed it into a model that could, for each burner on a site, have an estimation of the local progress of the treatment. That would mean that each burner would be aware in its vicinity of how the treatment is progressing. And you could pinpoint which burner needs to operate at which power. Some could even be stopped early, and so on.
Because it's all based on the heterogeneity. We know that despite the fact that we have reports that show a certain level of contamination in area, the reality on a smaller scale is way different. There are vast differences in moisture and contaminant content. So you would take advantage of that.
Remains one open point is, let's say you have this model at hand. It means that every hour, your model gives you an update on the set point, exactly how each individual burner should operate. It means that to your site operators, every hour you have to ask them to retune all of the burners of the site. That's, of course, not a way to go, which is why we are also exploring the autonomous burner. We are actually quite advanced on this topic, where we are bringing the Internet of Things to the burner. We are, with the custom hardware that we have designed in-house, we are able to provide the burner with an internet connection, which allows from anywhere in the world, thanks to the internet connection, to do remote startup and shutdown of the burner, to do remote power control, remote monitoring of all the key operating parameters, and of course be able to perform any diagnostics. And since it embeds all the electronics required, we can have a direct communication with this treatment model. So this update of every hour, it's quite straightforward to get an update on the operating parameters, automatically tune them, and have the burners actually react to his immediate surroundings.
And based on what currently the system reacts on what logic, what makes that burner react? Is it just deterministic based on what you decide on? If this, then do that, or how do they react?
The first step would be a deterministic approach because it's first of all easier to control, and as we are only entering this subject, we don't have yet the volume of data that would be needed to have a stochastic approach to bring some advanced.
But this would allow that to be done in the coming project.
Exactly. That's more on the thermal progress modeling side. The burner is already ready to adapt to every comment. Everything.
It's about how you provide the instructions, essentially. Exactly. It's what decides what instructions every burner receives. Okay. Yeah. And we don't have to send people to manually do that anymore.
So here is a bit of a zoom in on this burner. You can see it's not the prettiest picture, but it's a working device in which you have the proprietary hardware that is installed, and it's running the software that allows this communication between the model and all the sensors. So inside of there are hidden sensors that allow to maintain this. Actually, we are maintaining a combustion with a desired set points, which can be adapted, and it can react to its environment. So these sensors and these actuators perform internal control loops that you do not even have to worry about. You just put your set points in terms of delivered power, and the burner will do the job. Maybe just an illustration of because so far you can take for granted what I said. Here is it in action. I highlight two phases. On the left graph, you can see the exhaust temperature of the burner. If let's say I want to reach 200 degrees, you can see on the left graph that I'm stuck about 140. I'm slowly increasing. The burner is trying to push it higher. The injected gas pressure on the right is plateauing to its maximal allowed level. So it's pushing hard to reach the target temperature. To make it more interesting, we can lower this target temperature. This is phase 2. On the left graph, you see that we are trying to stabilize around 120 degrees. It's more interesting because you see on the right, on phase 2, that the gas pressure is dropping and auto-adjusting around the set points to maintain this given temperature. So that's a bit of a nerdy way to show you that it works. And I'm also happy to say that it is currently operating on a site. We thank our partner Lingeld, which is allowing us to deploy this on site. But so they are currently functioning. That's not only prototypes and lab tests. It is currently happening. Okay. Which brings me to my conclusion. Actually, I just want to repeat a few points that are really your take-home messages. We can improve the treatment efficiency by looking at indirect tracers and not only at the cold point temperature. To leverage this information that we can get, the way we do it are internet-connected burners that can automatically adapt to the new set points. And as a last point, tests are underway. It is happening.
Yeah, that last point is always the case. So we went from smart burners to very smart burners. So, well, thank you very much. I think it was a good introduction on the subject. I don't see exactly what the questions are. Maybe if we can, I have one overall comment on the, let's say, on the approach. When I look at it from history, I look at thermal efficiency, and what I call thermal efficiency is what's the percentage of the energy that we provide that is actually used to clean up the soil. And when we started, like, decades ago, we had rotary kilns and we had an efficiency of about 18%. It means that for every kilowatt hour, we had only 18% that was really effectively used to heat the soil and to treat it. Over time, it has improved dramatically, mostly by focusing on the burner, on the energy source, having less and less losses, because that was usually, if you have 18%, means that most of what you're heating is just the outside air or the outside or underneath, etc. So the latest numbers were about 80%, or the smart burners that were developed with the focus on combustion made it to the point that we were at 80% efficiency. Now this brings us farther, because it no longer plays on how efficient the burner is. We consider that we've reached a certain plateau there as well. But that now we just say, instead of needing 200 kilowatt hours per ton, we may do the same thing with probably 150 or 140. So we may theoretically go above 100% efficiency if we still calculate that the efficiency is the big cannon approach. The efficiency being taking the volume, the moisture, and then doing the thermodynamics to define how much it's needed. This would allow us to go farther and make sure that we can reach the goal, which is clean soil. And as you said in your introduction, I liked it. The goal is not per definition to reach the target temperature, but it's actually to clean up the soil. But we have evolved over time by just taking the temperature as the goal, and regulators like that because they can measure it. You reach it or you don't reach it. But actually, our overall goal is to clean up soil. So
yeah, you can have the most efficient burner in the world if you are using it to inject more into the clean soil.
Yeah, it's wasted energy anyway. How do you see do you think there is more? What's the order of magnitude you can see on improving there?
Well, I'm quite confident on the 20% that we have demonstrated in the lab. That's a safe baseline, I would say, and that's based on quite straightforward approaches. So would we be able to include more sensors to leverage a bigger quantity of data? We could possibly go for maybe a 10-20% even further. That would be my...
Because then the next stage is also to apply the heat at the right depth, which previous webinar explained how we could get like remote flame burners, so we could define also with that data at what depth do we need to inject the heat. Because right now it's just on the full length of the heater elements. It's not yet specific to some depth that you can adapt it.
It cannot be adapted on the fly, but as a matter of fact, the test that we are doing now is combined with the remote flame technology.
Okay.
So,
and you can also play on the fan speed so that it could also change a little bit of the repetition.
One potential improvement would be indeed to control the heat gradient along the tube. That would be a way to focus the power into specific depth on the fly.
Yeah. Okay. I see an overall question from Charlotte about the treatments that we apply. Indeed, most of our technologies that we apply at Hamers is thermal. That's where our history is. It's about more than 30 years. So it went from rotary kilns to in situ on-site treatment. We have developed other technologies that are in one way or another linked to thermal, like dynamic skimming, which is treating the L-napple either cold or with improvements of heating. And also there has been a few webinars about that as well, combining thermal with in situ chemical oxidation, combining thermal with in situ bioremediation. So there is always a thermal backbone at Hamers. That's essentially our DNA. That's what we've been doing for that long. That's where our technology core lies. But we don't believe that it will that as a standalone it can solve everything. The solution is often really something that is a combination. In some cases, standalone works, but in many cases, it's smarter to use it in combination with others. I mentioned combination with bioremediation is a good example where you use thermal to treat the source zone, and then you know that the groundwater will be heated anyway. And so in the plume, you heat up the groundwater just by residual heat up to 30, 35 degrees, which is perfect to boost bioremediation. For example, that's the moment where you would inject your bioremediation enhancers, or in some cases, chemical oxidants, which would then be thermally activated. So the overall answer is yes, we're a thermal company, but on the other hand, we're trying to combine it. PFAS, the latest ones we did with PFAS, is a clear combination between soil washing and thermal, which we believe is the best combination of both, where you handle most of it by soil washing, and then the filter cakes, which contain most of the PFAS, then you treat them thermally, and that makes it cost effective and also environmentally more friendly, because you reduce your energy consumption overall. I see no more question. Oh yeah, sorry. Oh, okay. That was not a question. I saw that. So anyway, let me then, I think, shut down the. Sorry.
Was the IoT implementation a big challenge?
Oh, okay. I'm getting older, so let me.
That's
let me
one
do this.
for me.
That's one for you. Go ahead, Mathieu.
I would say that the IoT part, actually, there is nothing groundbreaking in that. We are using quite regular electronics. Actually, the challenges in the electronics development were more linked to the very harsh environment that is in which operates the thermal resorption burner. To give a few examples, these devices have to survive in outside conditions for months without being serviced. And on the sensing part, there's quite a big difference in measuring the O2 concentration and measuring the O2 concentration in the exhaust gases of a burner that operates at 400 degrees. So that the biggest challenge was really on the reliability and harsh environment part. The standard electronics was relatively straightforward.
Yeah, the sensors, because the vapors contain moisture, contain a little bit of particulate matter, it contains, sometimes are quite corrosive, it contains a hell of a lot of, not only the contaminants we measure, but also the degradation products and the or the non-contaminants, that sulfur, sometimes fluor, some other compounds which can be harsh on the sensors. And I remember you told me all the sensors that we tried and which didn't work. So it's always good just to present those that work, but they were a hell of a lot but didn't work. So anyway, let me first of all, and thank you, Mathieu, for a pretty interesting presentation. If you missed part of it, it's, as I said, I repeat, it's going to be online pretty soon on YouTube. So watch it and share it with all of the people who may be interested. If you are interested in knowing or in applying these technologies or further thermal technologies or thermal combinations, we're open for business. Just contact us. As we introduced, we're operating all over the world, so we're there to study any of your projects and try to bring the most sensible answer to it. And I think you'd be surprised. Few announcements before we leave. Our next webinar will be 25th of May. We'll talk about the combination, we'll talk about again, between soil vapor extraction and thermal desorption, and it will be Jean René who will give that webinar. And in between then, if you have the chance to join us next week, we'll be at the Nicole workshop in Paris, for 2.5 days. Lots of topics to be discussed there. And the week after, there's I2T2, so in situ thermal resorption seminar in Banff, Alberta, Canada, where we also be present with, in part, also our US team. So rest me to thank all of you. Enjoy the rest of the day. For those who have a rest of the day, enjoy the morning, and see you at our next webinar in 2 weeks.
Bye, thank you.
Bye-bye.